Okay, so now we're going to go into our last subject in the evolution unit. Let me try to, okay. Oh, there we go. Try to enlarge this. All right, so we've gone over the process of speciation, how natural selection works, different forms of evidence for evolution. So now we're going to kind of tie it all together with this last subject, which deals with the evolution of populations and kind of taps into all the other topics we've gone over so far. And this is a really cool picture. So here it's referring to the evolution of certain types of whales. If you can look here, it says toothed whales. Things like blue whales and humpback whales, they don't actually have teeth like killer whales do. So they have a different evolutionary timeline, but this one is showing those that had teeth. And again, we've talked about before that they all came from land mammals that started going back into the water and became sort of like crocodile-like animals that just became, over millions of years, more and more adapted for surviving in the ocean. And if you look back, it definitely goes back millions of years. I guess the oldest killer whale or orca fossil that's ever been found is about 11 million years old. And we get back to the Basilosaurus, Durodons, and some of these other organisms. These go back, as you can see, about 50 million years. So, you know, huge amounts of time, allowing for huge amounts of change. And some of the things that we see in their fossils is, you know, sort of bodies that aren't really designed well for moving around on land. So this one's got like really skinny legs and kind of a really big body. So they think this one was, you know, swimming through the water maybe more, almost, you know, maybe more like a hippo or something. But even more so because the legs are much skinnier than a hippo's. And this one here, really not a good body for moving through the water. So they think this one is the descendant of, or the ancestor of some of these mammals that went into the water to hunt. And then we get things like the Durodon, where they actually have little feet kind of hanging off the back, and that show that they have ancestors that were on land. And even when we get into the much larger Basilosaurus, we see that they have little limbs coming off the back, which modern whales do not. And but we have talked before in a couple of our other subjects that in this area, most of the modern whales, or maybe all of them, have evidence or have bones that are hip bones that show that they came from animals that lived on land and eventually over time evolved into ocean animals. And those hip bones are still there because the DNA is still making those bones, but they're obviously not functional. And I even showed you guys a picture recently where those hip bones even have little toes at the end, showing how those vestigial structures have, you know, changed over time. And again, a vestigial structure goes back to 4-3 and is a structure that shows what things used to be. So it's a body part that maybe doesn't serve its original function, or maybe even has no function anymore. And in the case of the hips of whales, they have no function. They are literally just some bones sitting in their body that do nothing, but they come from the fact that their ancestors, like the Basilosaur and some of these other organisms, did have bones that represented their legs and their hips and eventually became vestigial. So let's get right into it. So first we're going to go over different patterns of evolution. And the patterns of evolution, they show us different ways in which evolution takes place. And so when we look at how populations evolve, they're going to evolve in generally some of these different patterns overall. And here's again another interesting picture of some whale ancestors, a different diagram. So here we're going back about 40 or 50 million years ago as we progress, and sort of long. They don't. I wish they had some more measurements here as far as their size, but sort of long, almost like weasel-like or otter-like bodies. And over time, they became this Rhodocetus, which really didn't have very good functional legs. So again, more like a mammal crocodile. And then about 45 million years ago, we think in where modern Egypt is now, the Protocetus, which I'm thinking cetus means whale. Yeah, it does, because I know ambulocetus means walking whale. So anything with cetus in it is a reference to whale. So proto means like before. Could maybe mean like new, but usually is like before. So it's basically saying before it was like fully a whale, they were protocetus. And I think that's because they weren't fully whales yet, because their nostrils were here, and we now know that those nostrils have moved back over time through natural selection and are more kind of above their head or their neck and allow them to breathe. And so, but in Egypt, they found these Protocetus fossils that go back about 45 million years ago and are believed to be the descendants of certain whale species. All right, there's a couple broad patterns that we can look at, and the broadest patterns show up in large cladograms that we've done before. And this is a really cool one because it's kind of showing some of the ancestors of mammals and things like that, and kind of branching into different directions with dinosaurs. And so it all goes back, here if we look about 286 million years ago in the Permian period, and then it goes through the Triassic, Jurassic, Cretaceous, and then the Cenozoic, which is much more modern. And we see a different, variety of different branching directions here. So stem reptiles, I think, is referencing like the first reptiles. And then we have some, I'm having trouble reading this, pelycosaurs maybe. This is typically referred to as like a Dimetrodon. So the Dimetrodons are actually believed to be possibly the ancestors of mammals and modern reptiles. I think it has to do with their skeletal setup and the position of their legs in relation to their body, and maybe a little more underneath and four-legged, as opposed to these like two-legged dinosaurs, and where their legs are a little more on the side. And then we get into the therapsids, which are pretty consistently considered the ancestors of modern mammals. And if you look here, we get this divide kind of, happened back in the Permian, where maybe you start to see the first mammals, which were just little small rodent-type animals. And after, hundreds of millions of years, we eventually get to the modern reptiles and mammals. We see there's a track here where they think sort of snakes and lizards broke off. Oh, so not just reptiles up here, turtles actually specifically. So I guess kind of making a little bit of a connection, if we go back hundreds of millions of years ago, between turtles and mammals. Not the same path as we see reptiles or other reptiles like lizards and snakes. The tuatara is really interesting. This is usually something I address. I have a picture of a tuatara in my classroom, and the tuataras are actually considered the only modern living dinosaurs. And they're small. They're about the size of an iguana, so I consider crocodiles much more like modern living dinosaurs. But in the case of the tuatara, it is said that they're the only reptile that currently exists that its skeleton has not changed since the time of the dinosaurs. So it's stayed the same. It hasn't had to evolve. Natural selection has not pushed it to evolve. And so based on that reason, the tuatara is kind of seen as the only organism maybe on Earth, at least as far as a vertebrate animal and a reptile, that is the same as it was back in the Jurassic and Triassic. And we see that it's split off, maybe a couple 100 million years ago, and they are found only in New Zealand, and so that makes them kind of a special reptile. And then down here, we see the thecodonts kind of evolved into crocodiles, and then eventually the dinosaurs also evolved into birds.